Hello everyone, I am Faizan Masood from Qatar University from Department of Civil Engineering. Today I'll be presenting our paper which is about the comparative evaluation of SQP and PSO in trust design optimization. I look forward to sharing our methodology, results, and key findings with you. Buses are everywhere and they consume a huge amount of steel in any project. Reducing even a few kilograms from each member can save us thousands of dollars. A lighter structure means lower material usage, faster fabrication, and reduced environmental impacts. We note that designing a truss is not straightforward. Uh, Truss members are highly interdependent, and we have to satisfy several constraints all at the same time. In practice, we usually follow a trial and error approach. We analyze the structure, choose a section, check stresses and deflections, then go back and change it again. This loop can go for hours or even days, and finding the best design manually is extremely challenging. This motivation is what led me to explore optimization techniques for truss design. Uh, the next question is why truss optimization itself is a challenge. First, every truss must satisfy strict stress and displacement constraints. Secondly, the truss members are highly interdependent. Furthermore, there are many optimization methods available, but there is no clear answer on which performs the best. And finally, the objective remains the same to minimize structural weight while satisfying all constraints. These challenges set the stage for my research, a comparative evaluation of different optimization methods. Based on the identified challenges, the objectives are to implement SQP using MATLAB's FPinCon along with genetic algorithm and particles farm optimization methods for truss sizing optimization. Second is to have a comparison of these gradient-based and meta-heuristic approaches. Third is to evaluate these methods using standard benchmark truss problems. And finally, to assess each algorithm in terms of minimum achievable weight, convergence behavior, and computational time. And now let me formally define the problem addressed in this study. The objective is to minimize the total weight of the truss structure. Here I have focused on size optimization, in which we can only change the cross-sectional area of the members. Each design must satisfy stress and displacement constraints. Additionally, practical lower and upper bounds are imposed on the member areas. There are two main families of algorithms, gradient-based and meta-heuristics. Gradient-based rely on mathematical derivatives, while meta-heuristic, they explore the design space more freely using rules inspired by nature. In this study, I have used three algorithms, each with a different personality. Let's start with SQP, which is a gradient-based method. Imagine you are standing on a mountain trying to reach the lowest valley. SQP looks around, estimates the shape of and slope of the ground, and takes a carefully calculated step downhill. And after each step, it reassesses the landscape and updates its plan. This makes SQP precise and efficient. But the catch is if the valley it finds is only a small dip and not the deepest one, it may get stuck there. Next, we have genetic algorithm, which is like nature. It evolves the design through trial, error, and adaptation. You start with a bunch of truss designs, each slightly different. You test all of them, keep the best ones, mix their genes to create new designs, and even add small mutations. Over generations, weak designs disappear and strong designs dominate. Because of this evolutionary process, it explores the entire search space. It can find hidden valleys that even SQP cannot. But it takes time because it tests many designs before settling for the best one. Finally, we have PSO, which is the most social algorithm of the three. It is inspired by birds flying in a flock. Let's suppose the birds are searching for food. Each bird explores on its own, but whenever one gets closer to food, it chirps and the entire flock starts moving towards that direction. In PSO, each bird is a design, and with every step, it adjusts its direction based on its best spot and the best spot found by any other bird. It converges faster than GA and need fewer parameters. This slide summarizes the main optimization methods for truss design and where my work fits. SQP is very efficient for nonlinear constraint problems, offering fast convergence and reliable handling of stress and displacement constraints. GA is widely used for discrete and multimodal design spaces and is flexible and powerful but is computationally intensive. Particle swarm optimization is popular for sizing and topology optimization with a good convergence and tunability. Beyond GA and PSO, researchers have explored many newer meta-heuristic algorithms such as political optimizers, CBSO, advanced simulated annealing. These methods perform well for larger or more complex trust problems. Comparative studies indicate that differential evolution frequently outperforms others in robustness and scalability. We also have hybrid methods which combine the strength of two different algorithms. Overall, a wide range of algorithms exist, but their performance depends on parameter tuning and problem complexity. So, how do we overcome the limitations of manual trial and error? Instead of adjusting each truss member and manually, the algorithms automate the design process. Uh, the approach is straightforward. We define the design variables, compute the structural responses, evaluate the objective function, and let the algorithm intelligently update the design. This cycle repeats automatically until convergence is achieved. The outcome is much faster as compared to the traditional manual approach. Now, to test this automated workflow, we need a set of benchmark problems. Truss is of increasing complexity. We start with 10 bar planar truss. It is a classical benchmark problem, simple and well studied. Uh, it has 10 different design variables, and the area of each can vary between 0.10 to 35 inch square. We have two constraints here, displacement and stress. We have a load of 100 kilonewton applied at nodes 2 and 4. Um, at the end, we have the parameters that we are using for different algorithms in MATLAB. This slide summarizes the optimization setup for 2D 17-bar truss, which is more complex than the previous one. This truss has 9 nodes and 17 elements, with each bar's cross-sectional area treated as an independent design variable, giving us a total of 17 design variables. The areas can vary between 0.1 and 50 inch square. The design constraints of stress and displacement ensure safety and serviceability. Uh, at the bottom, you can see the parameters chosen for the three algorithms for this problem to balance solution of accuracy and computational efficiency for this more complex truss. Lastly, we have the 25 bar 3D tower truss. It has 10 nodes and 25 elements. The elements are grouped into sections. So we have 8 different independent design variables. The area of varies between 0.01 to 35 inch square. The compressive stress limit is uniform, while the tensile stress is different for all the design variables. The structure is subjected to two independent loading conditions, which adds to the complexity. So by testing across these problems, we can evaluate each algorithm in terms of weight reduction, success rate, and computation time. To determine which algorithm performs the best, we had three key performance measures. GA and PSO were tested on all three truss problems 10 times to reduce randomness. Our first performance measure was weight, which was our main goal. Second was constraint satisfaction. And finally, the third was the time it takes to converge for the algorithm. The optimization results for the 10 bar problem, a 10 bar truss problem demonstrate the performance of three algorithms used. All algorithms produced fully feasible designs, satisfying the constraints. In terms of accuracy, both SQP and PSO were able to converge to the nearly best known solution from literature, highlighting their precision, while GA produced heavier results and showed more variability across runs, which is typical for a population-based evolutionary algorithm. SQP is the fastest here, followed by PSO, while GA needs some time to converge. These graphs show that all three algorithms converge to a similar minimum structural weight, but with different convergence speed and robustness. SQP curve starts from a low weight and rapidly increases to a feasible design. Uh, GA curve shows 10 independent runs, all starting from high weight stand, gradually decreasing towards the optimum value. Convergence is slower and more stochastic, but GA explores the design space broadly. PSO runs also start from high weight and drop steeply, reaching a near optimal weight around typically in fewer than 40-50 iterations, uh, which is faster than GA. For 17-bar truss problem, all algorithms achieved 100% design feasibility. Uh, SQP and PSO both gave accurate results, virtually identical to the best weight from literature. This indicates that these algorithms are highly precise and effective. GA, on the other hand, yielded slightly heavier results. This reflects the stochastic nature of GA and its tendency to explore the design space more broadly. SQP remains the fastest. PSO required about 15 seconds, while GA was the slowest at over 30 seconds due to its iterative evolution. This slide shows the convergence history of 17-bar truss problem. Here, GA shows a very sharp initial drop, shredding most of its weight within the first 25-50 iterations. Um, PSO converges much faster in terms of iteration count as compared to GA. It reaches the stable minimum in 60-70 iterations, and the stair step in PSO indicates that this farm is finding a new local optima. Uh, SQP, the graph of SQP is most distinct. Unlike meta-heuristic, SQP appears to start from a low, potentially infeasible point and increases the weight to satisfy the constraints. For the 3D truss problems, all three algorithms satisfied the constraints, get achieving 100% design feasibility. SQP produced the most accurate results, followed by GA and PSO. In terms of computational efficiency, SQP is the fastest, followed by PSO, while GA is the slowest. The results highlight how algorithm choice affects both performance and computational cost, especially as complexity increases. This shows the convergence history of 25-bar truss tower. The GA chart shows a sharp initial decrease in weight within the first 50 iterations. Uh, there is a visible spread between the 10 runs during the middle phase. It requires more computational effort as compared to PSO and SQP. Unlike GA, the turn runs of PSO are extremely consistent, with all paths merging by the 75th iteration. The stair step here also suggests that the swarm is discovering better regions. SQP starts from a very low weight and increases the weight to satisfy structural constraints. Additionally, structural design relied heavily on manual trial and error approach. This process is very time consuming. So modern optimization methods transform this by automatically evaluating thousands of design alternatives. As a result, optimization represents a critical advancement in structural engineering. Based on our results, SQP is the fastest. While it is best for well-behaved problems, it can struggle with extreme nonlinearities like buckling or conflicting load cases. PSO delivers results that are as light as as SQP, and GA explores this design space more widely. The critical point of my presentation is that no algorithm is inherently bad. Their performance is dependent upon parameters. Fine-tuning these parameters could potentially match or exceed their current performance. For future work, this optimization framework can be extended to a full-scale 3D steel structure. Another approach is integrating optimization algorithm with commercial finite elements tools like SAP 2000s or research platforms like OpenSea's using APIs and Python-based optimizers. The ultimate goal is a fully automated system that produces a material efficient, safe, and sustainable design for real world problems. That's it from my side. Thank you very much.